In this lecture, we are going to look at the Colab notebook that performs linear regression in order to prove Moore's law is true, that the transistor count doubles approximately every 2 years. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. To start, we're going to have all the same imports as before, with one additional import, which is pandas. Pandas is useful for working with CSV files, which is the format our data happens to be in. To obtain the data, we are going to use the wget method to get the CSV file hosted on my GitHub. Next, we are going to load in the data. The data doesn't contain any headers, and it only contains 2 columns. I would recommend verifying that this is the case. The next thing we want to do is reshape X so that it's a 2-dimensional array of size n by 1 rather than a 1D array of length n. We also need to do the same thing for Y in PyTorch, although this generally doesn't extend to other libraries. Remember that the convention is X is a 2D array of size n by d, and Y is a 2D array of size n by k, where k is the number of outputs. Next, we are going to do a scatter plot of this data. Notice that it shows exponential growth, which we already know. So next, we're going to take the log of y, which is what we discussed previously. We see that we get back what looks like a good candidate for linear regression. Next, we are going to do a little bit of pre-processing on the data. Specifically, we're going to standardize or normalize x and y. We'll want to keep these means and variances around for later use. So let's call them mx for the mean of x, sx for the standard deviation of x, and similarly for y. What we have to keep in mind is that, by doing this, the units of x and y no longer make sense. Previously, x had units of years, but this is no longer the case, and y had units of log counts, which is no longer the case. We'll have to reverse the transformation later on if we want to get back to the original units. In the next plot, we do a scatter plot again, which on first glance looks exactly the same as it did before. But if you look closely, you'll see that both the x and y axes are centered around 0, and the range of values is now small, which is exactly what we want. Next, we're going to do a little more pre-processing to convert our data into float32. Next, it's time to create our linear regression PyTorch model. Thanks to our rule, all data is the same, this code will be exactly the same as before. Once we have our model, which is just one line of code, we're going to create our loss and optimizer. As you can see, there's one argument here that might be new to you, momentum. This is one of those variations on gradient descent that I was talking about earlier. If you want to know more about these, you're encouraged to check out the in-depth section of the course. Next, we're going to convert our NumPy data arrays into torch tensors using the from NumPy function. Next, we're going to run our main training loop. As promised, this is the exact same thing as what we had earlier, just with a different number of epochs. I just want to mention again, because a lot of people ask me, how do I know what number of epochs are needed? Just remember that there is no way around trial and error. There is no magic formula. You just have to keep trying until your loss per iteration looks right. You'll be seeing the same loop over and over again throughout the course, so each time I'm going to spend less and less time explaining it. Alright, so from the loss values it's printing out, it looks like the loss has converged. Alright, so next we're going to plot the loss per iteration as usual. And from this we can confirm that our loss has converged. Next, we're going to plot our line of best fit. Again, this is the same as before, so there's no need to explain this code again. As you can see, our line is indeed a line of best fit. Next, let's get the trained weights of the model. You already know how to do this. It's model.weight.data.numpy. As expected, it's a two-dimensional array that holds a single number. The question is, what does this number even mean? To answer that question, we need a little theory. Let's start by recalling our model of exponential growth. We have c equals c naught times r to the power t. As you recall, we convert this into a linear equation by taking the log of both sides. So now we have log c equals log of c naught plus log r times t. If we rename the variables, we can make this look a little more familiar. So let's call the input x, the output y, and the slope a. A good thing to remember is that the slope of this line is the log of r, not r itself. We can leave the intercept term untouched because it's not related to the rate of growth. It's just the initial value of the count. Next, we have to take into account that our data is normalized. As you recall, we normalize the data using the equations we see here. Let's call the transform data x prime and y prime. So y prime is equal to y minus my divided by sy, and x prime is equal to x minus mx divided by sx. Now we can begin to understand our own model. Our own model is also just a line, just with different units and therefore a different slope and intercept. So let's call the parameters of this line w and b. So the line that we actually fitted would be y prime equals w times x prime plus b. What we can do next is recover our original model by substituting x prime and y prime with their expressions in terms of the original variables x and y. So now we have y minus my divided by sy is equal to w times x minus mx divided by sx plus b. You should be able to see intuitively that this is still a linear equation. After doing some algebraic manipulation, we can isolate y in terms of all the other variables. If you don't understand how we got to this step, I would strongly recommend trying this on paper by yourself. What we can see is that there is one term involving x and three other terms not involving x. Clearly, the three terms not involving x are equal to the intercept log of c naught. Remember, we don't care about that because that doesn't involve the rate of growth. Instead, what we care about is the slope. Luckily, it has a simple expression. It's just w times sy divided by sx. We know that our original line has the form ax plus log of c naught, and therefore we can conclude that if we had fitted a line to our original data, the slope would be a equals w times sy divided by sx. Alright, so the next question we want to ask is, what is the value of a? Luckily, we know w, we know sy, and we know sx. So we can just plug them in to find a. Remember that w is a two-dimensional array holding a single value, so in order to retrieve this value, we have to index w twice, at row 0 and column 0. We see that we get another sort of strange number, 0.34. It's not clear how this would lead to a rate of growth. That means the transistor count doubles every 2 years. Of course, that's because there is still more work to do. So let's go through a quick calculation. To review once again, our model for exponential growth is the count c is equal to c naught times r to the power t. C naught is the count when t equals 0, and r is the rate of growth. If we take the log of both sides, we get an equation that's linear in t. We can express this in terms of our usual linear regression variables, y equals ax plus intercept. This shows us that y is equal to log c, a is equal to log r, x is just the time t, and the intercept is log of c naught. Because a is equal to log r, we can just take the exponential of both sides to get that r is equal to e to the power a. From here, we can plug in the value for the slope that we found to get that r is equal to 1.407. Although, as you'll see, we won't need to use this value directly. Next, let's consider the doubling time, or in other words, how long it takes for c to double. We can do this by thinking of the original equation as the original time and the original count. This origin is completely arbitrary, and as you'll see very shortly, its values don't actually matter. So in order to double this count, the left-hand side would become 2c, and on the right-hand side, the time would just be t prime. We call it t prime because we don't know what it is yet. That's what we're trying to solve for. So if we take these two equations and divide one by the other, we see that the c disappears. The c naught also cancels out. And as I promised, the origin point doesn't matter. We get 2 is equal to r to the power t prime minus t. T prime minus t is actually the time duration that we care about. That's how long it takes for the transistor count to double. How far from t is t prime? We can rearrange this to get that t prime minus t is equal to log 2 divided by log r, which is equal to log 2 over a. Since we found a, this is just a number. And more importantly, it's a constant number. One important note is that the defining characteristic of exponential growth is that the growth rate does not change over time. In other words, the value of t itself doesn't matter. This same equation holds no matter what the value of t is. This is like saying the duration from t to t prime is always constant, and as you can see here, it's always log 2 divided by a. So in the next block of code, we can print out this value. Log 2 divided by a is approximately equal to 2, just as Moore's law says it should be. Therefore, we've confirmed that Moore's law is true. In the final block for this notebook, I have a little exercise for you. In this lecture, one of the most difficult parts was transforming the data using standardization and then reversing that transformation. And you might ask yourself, is that really necessary? So the exercise for you is to find out what happens if you don't try to normalize the data. You might assume that since the data falls on a line, it should be pretty easy to apply linear regression, as we've done multiple times so far. So give that a try, and I'll see you in the next lecture.